Okay, let's look at Le Chatelier's principle and see the influence of this principle on equilibrium reactions. So first of all, the principle says that if a system at equilibrium is disturbed, then the system will adjust itself so as to minimise that disturbance. Now there are three types of disturbance that we can have. We can either disturb the concentration of the reactants or products, we can disturb the temperature, or we can disturb the pressure. So our first scenario says that if we disturb the concentration and we increase that concentration of either a reactant or product, the reactant will move to minimise that increase. And conversely, if we decrease a reactant or product, the system will move toward that decrease. In other words, it'll increase what's been taken out. Let's look at that in context. So we have a reaction between arsenic acid, iodine, water to give us arsenic acid, our hydrogen ions, and our iodine ions. Now, according to Le Chatelier's principle, if this is at equilibrium and we increase one of the components, it should shift away from that increase. So if we increase the arsenic acid, we should actually see the system move to decrease this. So yes, we'll see a decrease there, but we'll also see a decrease there, a decrease there, an increase of our product, because we're trying to get rid of this, or the reaction's trying to minimise that increase. We'll see an increase here and an increase here. And overall, the reaction will move in that direction, in the right-hand direction. On the other hand, if we decrease the amount of arsenic acid in the system now, in other words, we take it out, we find that we'll get an increase in our reactants and a decrease in our products. And we find that this one, the reverse of this process, the reaction will move in the left-hand direction. Let's say we now increase the pressure in the system. Well, Le Chatelier's principle says that an increase in pressure will move the reaction to minimise that increase. So if we have reactants involving gases, the system will try to relieve that pressure in the system. The reaction will try to relieve that pressure in the system. Conversely, a decrease in pressure will move to restore that original pressure. So let's take an example. If we've got PCl3 as a gas, we react that with chlorine gas to give us PCl5, and let's say we increase the pressure. Well, if we count the number of moles on the left-hand side, we've got 2, and on the right-hand side, we've got 1 mole. So the system, with this increase in pressure, will move to the right-hand side, because we've only got 1 mole here, whereas we've got 2 on the left-hand side. So what we'll find is the concentrations of both of our reactants will decrease, and the concentration of our product will increase. If we were to decrease the pressure in the system, what we'd find is that the system will try to restore that pressure, so we'll get an increase in our reactants and a decrease in our products. Finally, if we were to manipulate the temperature of our system, we'll find that an increase in temperature will move the reaction to absorb that energy. So whether you've got an exothermic or endothermic reaction, it will either shift it left or right to absorb that energy. So if we've got carbon, we combine that with water to give us carbon monoxide and water as a gas. If we increase this temperature, and this is an endothermic reaction, so it requires energy. So if we increase the temperature, we increase the energy. This will push the reaction in the right-hand direction. On the other hand, if it's an exothermic reaction and we increase the temperature, it will push it in the left-hand direction. Let's look at this applied to something a bit more real world. This is where we force a reaction to completion by manipulating one of those three or all of those three components that we've just talked about with Le Chatelier's principle. We have a common reaction. Nitrogen plus hydrogen gives us ammonia. Now, ammonia is a very common precursor to a lot of things that we use in industry, but it's not easy to produce. So if we were to use Le Châtelier's principle to increase the production of ammonia, it would be quite cost effective. Let's see what happens if we increase the temperature. Well, from Le Châtelier's principle, if we increase the temperature, this being an endothermic reaction, will push the reaction in the right-hand direction. Similarly, if we increase the pressure, the system will work to decrease that pressure. So we have 4 moles of gas on the left-hand side, 2 on the right. So the increase in pressure will force the reaction in the right-hand direction to minimise the number of moles of gas that we've got in the system. So an increase in pressure will also force this reaction in the right-hand direction. Finally, if we remove the product, ammonia, the system will be forced to produce more ammonia. So by removing the ammonia out of the system, we once again force the reaction in the right-hand direction. Now Haber realised this, and this process is now used commercially in to produce high yield ammonia as a precursor to many other compounds. So this process is known as the Haber process for ammonia production, and is a wonderful example of utilisation of Le Châtelier's principle to produce a desired product that's not normally formed.